Hello everyone, welcome to another semester of electromagnetics at Wilkes University. This is the first lecture of a series of lectures that I'm probably going to be doing in this video format for you, kind of just to save time during our laboratory experiments. I guess welcome back from your break. So I'm going to start off by going through a couple of pieces of terminology. Now, I'm just going to read these right now, but I'll explain them in a little bit more detail as the slides progress. So, antenna pattern, plot of the directional dependence of the strength of radio waves emitted by the antenna. dBi is a measure of power relative to an isotropic radiator. dBd is a measure of power relative to a dipole. Antenna gain is a measure of how well an antenna can radiate energy in a specific direction. And this is intimately related with that antenna pattern, which is the first piece of terminology that's on this list. So antenna patterns. So to start off, I'd like to explain, a very basic concept in electromagnetic systems, and that's antenna patterns. So what you're seeing here is you're seeing both a 2D and a 3D radiation pattern of a very small patch antenna. It's not actually a very good antenna, it's just kind of okay. You'll notice that if you look at the plot here, I have two items that are listed. One is blue and one is red. The blue is directivity, the red is gain. So the gain is only a little bit, like maybe 2 dB, or 2 dBi, right? The directivity, though, is much, much higher. The reason why this occurs, and this happens a lot with different kinds of antennas, even well-designed antennas will have a difference between their directivity and the gain. The directivity is the absolute radiation of that antenna. Gain is kind of the directivity times some kind of a loss factor, or an efficiency factor. So in this case, my antenna is kind of lossy because I lose, a pretty considerable amount of gain on this antenna. But if you look here, this is a polar plot. Okay, so I guess I'm getting ahead of myself. This is a polar plot. And so what you're looking at is how much energy is radiated this direction or this direction based off of its angle. Now you'll notice that this line that's around my 3D pattern, this is the far-field cut that I performed for this antenna, right? So what you're actually seeing is effectively this curve is this curve, right? So think about it this way. The front of this antenna has a gain of about a little over 1, almost 2 dBi. The back, somewhere between -29 and -19. I'm not exactly sure. It's probably around -25, something like that. The point is that it's not radiating very well this way. Right? As we all know, in log magnitude, if we're 30 dB down, we're about 1,000th of the energy. So we're around 25, so let's just say we're about a 500th of the energy content of the directed radiation up this way. Right? So that's pretty considerable, isn't it? Right? So what we're interested in doing with antennas is we want to make sure that the energy is directed in the way that we want it. This particular antenna is designed as a fairly low gain directional antenna, right? So it's directional, it has fairly low gain, but the energy is, effectively pushed in a preferentially in one particular direction. You can kind of see this on this 3D pattern as well, where that's the back end, this is the front end, this gap in the center is actually where the patch antenna board is, right? That's why you have this null that's right here, because it doesn't radiate very well end fire off of the edge of the PCB, right? Lots of other antennas behave very similarly to this, but the reason why I'm showing you this is because I want you to get a handle on the fact that I'm going to show you a couple of different pictures, but they're always, all of these different ways of, describing antennas or looking at how antennas are just ways of visualizing so that you can get a handle on exactly what the antenna is doing at any given time, okay? So, remember I said earlier that gain of antenna is kind of an important concept? So antenna gain is different than the standard gain you get in most other electronics courses. Specifically, antenna gain doesn't mean that you're actually adding any energy to the system at all. As a matter of fact, what you're doing is you're just preferentially sending energy one way versus another. So like in this case, this is another 3D pattern. You'll notice the back lobes here are blue, which means that there's less energy going this direction, and the heat map shows red up here, which means it's putting a fair amount more gain up here, but it has kind of an interesting look to it. However, again, this is in dB. This is actually probably a fairly good directional antenna. It's hard to say for sure because I don't know what the characteristics are. This antenna here is an omnidirectional antenna. Right? Now, the reason I'm saying it's omnidirectional is because in some particular plane, if you remember going back up to this one, I cut it this direction. If I were to make the same cut that you see here on this antenna, then what you'd see is effectively a circle. Right? That's actually pretty good for an omnidirectional antenna, assuming that you're in one plane. Right, and you can kind of figure out why this antenna might look like that, because this right here that you're seeing, this is actually the antenna, and it looks kind of like it may be like an inverted F type antenna. This antenna is very popular for cell phones because it can make a planar. This is the ground plane for that antenna. This is the actual radiating element, and it can make it very small, and you can make it fairly omnidirectional, which is what you want for a cell phone, since a cell phone can be moving all over the place and seeing lots of other towers. Right, so you want an omnidirectional antenna. Now you might be, if you haven't seen this kind of thing before, you might be thinking, well, if I want an omnidirectional antenna, why wouldn't I just go for something that's really omnidirectional, like something up here, right? So this item here that you're seeing is a representation of what's called an isotropic radiator. Now I spoke a little bit about that earlier with dBi, decibels relative to an isotropic radiator. But the idea behind an isotropic radiator is that it is a theoretical perfect antenna. 100% of the energy that is present at the dot in the center is radiated into space. So one way to think of it is that as the waves move away from the center, it's kind of like blowing up a balloon. You know how the balloon starts stretching and stretching and stretching as it gets bigger and bigger and bigger? Well, the same thing can kind of be said about the electromagnetic waves that are coming off of, like an isotropic radiator, or for any radiator for that matter. The idea is that the energy is spreading out, and it's, as it's getting spreading out, you're getting an energy density on the surface of whatever the shape is that you have, and that energy density is getting less and less and less as you get further and further away from the source. So remember, this is a sphere, so that's going to come back into play when I start talking about Friis's equation down below. But this concept of how energy is formulated is where we get the idea of free space path loss, which is again something I'm going to go over a little bit more thoroughly in a bit. So I'm going to move on to the next one. Now another thing that's really important for antennas is ground reference, right? So in this case, what you're looking at is a dipole that's been moved at different heights above the ground that creates different kinds of reflections. The idea here is that you're looking at, basically the ground is below down here, and it's kind of reflecting up, right? So when it's an eighth of a wavelength off the ground, most of it's reflected up, and it kind of goes like this. Well, as you move it up a little higher, a little higher, a little higher, you start getting these extra lobes in elevation, right? So this is kind of like instead of looking at it like we were before, which was around the center, we're now looking at it, here. So this is where we would see like the donut. So if you took this 1/2 wavelength high, this would look very similar to this, right? If it was revolved. Just imagine that this is revolved around in this plane, in the XY plane, right? And imagine that's the Z. So this is the kind of thing that happens just because of where the antenna is located near a ground plane. Now the ground plane could be the ground, it could be a metal plate, it could be a lot of different things. But antennas are heavily affected by the energy, by things that are in their field of operation. So when we're doing these antenna tests in the class, you're going to find that you personally just standing around the antenna actually affects the pattern. Right, which might be kind of cool, but you can also look at it like, you're getting hit by some small amount of radiation, which, trust me, it's harmless, but it is something to, be conscientious about, that these waves are actually going through the air and that you are actually interfering with them, right? So there's several different kinds of antennas, and I guess I could have done this slide a little sooner, but primarily you have wire antennas, planar antennas, and waveguide type antennas. So wire antennas are like this antenna here. This is what's called a Yagi antenna, It's a highly directional antenna, and the idea is that right here is where you have your drive. So your RF drive, you can actually see the feed point here. There's a reflector element here and several directors going forward. Now you can actually make these things longer and longer and longer, and if you do the taper correctly and you set some stuff up, you can get pretty, extremely high gains with these types of antennas. That's why these are common antennas that you might see for, like, your TV, especially since they're again, very easy to construct. Now your TV antenna might look a little different because it might have a bunch of different sizes and shapes around it, but effectively it's just because it's trying to be able to tune to more than one frequency. Most types of antennas that are done like this and like this rely very heavily on the frequency of operation determines very thoroughly what the dimensions of the structure are. And because of that, they tend to be fairly narrowband unless you do some interesting things. So like in the case of this one, this is a patch antenna again, and actually you might notice that this is the same 3D pattern that we had up above when I was showing the 2D. This is actually a current map of the antenna as it's operating. If I made this a GIF, you would have been able to see that energy is fed through here, and then it moves in the center, and then it radiates out the side. This type of pattern is what you see with most types of patch antennas. And again, that's kind of the 3D pattern, but this is a planar type antenna. And again, this is a very, very small amount of bandwidth on this antenna, just like there's a fairly small amount of bandwidth on this antenna. This is a waveguide antenna. Now, waveguide antennas are a little interesting because waveguides can actually radiate all sorts of frequencies above their cutoff. The same is applied with waveguide antennas as a whole. However, they get worse and worse and worse as you get outside of their dimensional band of operation. One of the antenna that we're using in class is actually an AH-118 broadband horn. And when we get into class, you'll be able to see it has some really interesting structure. It's called a dual-ridged horn, and it's got a lot of extra stuff in there to allow it to operate over a much wider bandwidth. So the horn that you see right here, this is likely an X-band horn. That's just kind of an estimation, and it's based on the fact that this is probably an SMA connector, and I'm pretty confident of the size. The antenna that we're actually using in class, it goes from 1 gigahertz up to 18 gigahertz. This one has a cutoff that's probably in the 6 or 7 gigahertz range. So it's only a one band of operation. However, it will do multiple modes, and we'll kind of get into that a little bit later in class. But this is one of the simpler kinds of antennas to use or to make. So these have been very, very, very popular for a number of years. Planar antennas are really easy to simulate and really easy to fabricate, and so these have come into a fair amount of use as of lately. Wire antennas are a little bit more complicated. They tend to be larger, but that's primarily due to the frequency that you tend to operate them in. This is much higher. This here is probably a what says UHF, so it's probably something between 300 megahertz and 600 megahertz, somewhere in that range. It's hard to say. I'd be willing, well, I guess it could be a little higher. This could be like a 900 megahertz antenna. It's hard to say. I don't have any reference. But the point is, though, is that this is a much lower frequency than this, up at around 6, 7, 8, 9 gig. This one right here is actually designed to operate around 2.45 gigahertz. So again, it's another kind of higher frequency antenna than what you see for these wire antennas. So another topic that we need to talk about is polarization. Now there's two primary types of polarization. That's linear and circular. Now linear is broken up into horizontal and vertical, and really what the polarization has to do with is the direction that the electric field is oscillating in. So if it's oscillating in the Z direction, assuming that that's up and down, like vertical in front of you, then what you can imagine it being is that is a vertical polarized antenna. If it's going left to right, in the XY plane, then it is considered a horizontal polarization. Now, circular polarization is an interesting thing, and basically the idea behind circular polarization is that you make two feeds to the given antenna. One is 90 degrees out of phase with the other one, and what it does is it creates effectively a swirl around the path of propagation, kind of a spiral. Elliptical circulation is basically circular polarization, just not circular. Like, you'll notice that an ellipsoid is like a circle, but it's not perfectly circular. Now there's also left-hand and right-hand circular polarization, and those a circularly polarized or a linear antenna can receive a circularly polarized signal. It'll be down, approximately 6 dB. But if you have a horizontal and or if you have two linear antennas, one's horizontally polarized and the other one's vertically polarized, they'll be 30 dB down. Right-hand and left-hand polarization will be 30 dB down. I'll kind of go into this a little bit before class starts, but the idea behind, one way to think about it is that if your antenna is oscillating up and down and your antenna is facing this way, then you'll notice that less of the energy is going to be absorbed by something in that particular plane versus this plane. Alright? So again, I'll be able to answer any questions about this thing when you get into class. So another concept to think about when we're talking about antennas is near field. Now this is something we're actually going to deal with directly in our first lab. And so the idea behind a near field is that there's a portion of the antenna where effectively the wave fronts that are being emitted by the antenna are in what's called the non-radiative near field. And this is where you have a lot of destructive interference from waves that are like in a parabolic, they're bouncing around, from the feed to the outside of the panels, or, find an antenna array, they're just kind of too close and you're getting a lot of overlap. Once you get to a point, a delineation called the radiative near field, this is where you can actually start making antenna measurements. And this is often where you'll find near field probes taking their measurements of antennas. But we're not going to get into that because that has a little bit more complication, especially with the processing, than a standard far field system. So the idea behind a far field antenna is that the waves have gotten to a point where, as they're radiating away from the source of the radiation, the point at which they're here, now this line that's right there is effectively a wall, meaning that the phase front or the waves are planar to the surface of whatever it is that you're measuring out here in the far field. This is why we like to measure antennas in the far field, because we can assume planar waves, which means we only need a single point to measure. I can put an antenna source receiver, like say right here, and it'll be right on the edge of this wave, and it'll get the energy coming from this wave at that direction, and I can sweep this antenna over a given range and get a volume, and I can get a really nice, clear far field cut of the antenna source. Also, that's what those antenna patterns that I showed you earlier, those are all far field patterns, because you can simulate what this will look like in the near field, but when you're operating these antennas, primarily you're not going to be operating in the near field, you're going to be operating in the far field. Now, it's not to say that there aren't applications for near field, but that's really not what we're going to be going over in this course. So a key mathematical formula to remember here is the distance must be less than 2d squared over lambda, where d is the largest extent of one of the radiating antennas. Now, you could say that it's of the radiating antenna, but if you're measuring a very small antenna with a larger antenna as your receive antenna, as we'll be doing in this lab, you need to look at the largest size antenna that you have, because the far field is going to be the same. You still need to figure out what the far field is for your receiving antenna, just like you'd have to do for what your transmitting antenna is. So just keep that in mind as we're going through the lab, because that will become important. So again, far field is where we have plane wave interaction. It's easier to calculate, and it's where they're designed to operate. Now, this is another way of kind of viewing how everything works. So the intrinsic impedance of free space is approximately 377 ohms, right? So as you're in the near field, your wave impedance is going to be much, much higher. But as you get further, as you get farther and farther along into the near field until you reach this point, which is the far field, then what you're getting is it goes from around 5K all the way down to 377 ohms, or from 0 up to 377 ohms. These two different items are the positive and negative passing, or the magnetic field and the electric field, of the wave as it's moving along. And again, you can kind of visualize this cone as part of the reason why we try to do our measurements at the far field. It gives us a nice little point. So the Friis equation. So this governs the interaction of antennas in the near field versus far field. And the idea is that you want to look at how much power would you have received at some distance from an antenna. So there's a number of different terms that are in here. This is power received. This is power transmitted. This is the gain of the transmitting antenna, the gain of the receiving antenna. This is your wavelength. 4 pi r is the distance between your transmitter and your receiver. Now, and squared. So this is the original formulation for the Friis equation, and if you were to calculate it out this way, you need to know what your power was in watts, you want to know what your gain is, but not in dB. You'd want to know it as a linear value, and then you want to know your wavelength, and you could calculate it this way. A more convenient form, especially for the calculations that we're going to be doing, is this formulation. So this term right here, 1 over 4 pi r squared, right? If you were here, I'd ask you where you might think this might come from. But the idea is that 1 over 4 pi r squared, comes out to the surface area of a sphere. And so what you're looking at is you're looking at a term that is, the surface area of a sphere, and as your radius increases, the amount gets lower and lower and lower that you're actually, or that the surface, the power density is going to drop off as a square of these, or as the 1 over r squared of the sphere as it's propagating away. So this whole term that's right here in 10 log 10 and this number, this is actually just what you would call free space path loss. Now the reason why we have to look at a couple of other things here, like the power transmitted, that tells us effectively what we transmitted. The gain of the transmitting and receiving antenna make a difference because, again, remember how I said that the energy is preferentially being pushed in one particular direction with radiation patterns. So if that's true, then as your gain increases, you're going to be able to go further and further and further due to the fact that you'll have more energy available to drop off due to this term that is getting smaller and smaller and smaller as your radius is increasing. Right, so this one you can consider as a variable, and the rest of these are constants. And so basically, the further away you get, again, the less received power you have, which makes sense. But this is the mathematical formulation for why that happens. You actually have to use this formula in the lab as part of the experiment this week. So again, it's governed by the interaction of two factors, so it's geometric, and I kind of went over this a little bit, but it's the inverse square law, and the frequency dependence of the aperture, right? So in this case, we have, our gain, lambda squared over 4 pi, and this is the area or the aperture of the antenna. Now, the idea behind that is that the more aperture we have, the more energy we can collect of this radiating, propagating field. Again, that's why in the lab you're going to be asked to integrate over a surface of a patch antenna to get the total average power that you should see in a given location, because you're looking at it as it's the aperture of the aperture of the antenna, and it's the surface area over which the energy is being collected that is coming towards you. Right? So this is kind of a simple diagram of an antenna measurement system. Signal generator and receiver. This is very, very, very similar to what we're going to be doing in this lab. So you're going to have a signal generator, you're going to have a horn antenna, you're also going to have a patch antenna and a receiver. And you'll see why how this is useful when we get into the lab, but the idea is that you're basically going to be injecting a signal and then measuring that signal for power at different distances, at different translations, in different positions in front of the horn. I think you'll get a little bit better of a handle out of a system like this once we kind of go through the lab exercise. So this is the first lecture like this. I guess I'll be there to answer any of your questions when you get to the lab. So if you have any questions over this lecture, feel free to write them down, and I will do my best to answer all of them once you come to class. So until lab, good luck, and I'll see you there.